Sticking with the subject of astrometric microlensing with Roman, he will present a public code and a perspectives for detection. So take it away, Valerio.
Okay, thank you very much. So I'm Valerio Bozza from the University of Salerno in Italy. I've been collaborating with the microlensing science investigation team about the development of software for the analysis and computation in microlensing. So I will tell you something about the work we have done in the last few years. So uh, and in particular, I will focus on astrometric microlensing. So you already had an introduction by Chris about astrometric microlensing. So we know that we will mainly detect microlensing events through photometry because there is amplification of the flux of a background source from a lens. And we know that actually the individual images that are created by gravitational lensing have a very small separation of the order of 1 milliarc second. So in general, they are unresolved unless we use some special interferometry such as VLTI, which has been recently used in on a microlensing event. So, but this is a perspective that we are not going to speak about now. Now, the motion of the centroid of the two images described by an elliptical trajectory in the case of a single lens, single source, as was shown by Chris before. And this can be described by a very simple analytical formula. What is interesting here is that the maximal shift that we have in this elliptical shape is related to the angular Einstein radius. So this is an opportunity to measure the Einstein angle by an alternative channel. Now, this has already been demonstrated in a number of cases, and this is one of the most recent ones. Just two papers that appeared in the last few days about the observations of a microlensing event that was discovered by Moa and Ogle, and was later observed by the Hubble Space Telescope, which was able to measure the astrometric deflection due to this black hole. And in this case, it was possible to state that the lens was an isolated black hole of several few solar masses. So if Hubble can do it, also Raman can do it, of course. And this is just another cartoon that you can see that showing a simulation of what Raman should see with its pixel scale size and its PSF. But in order to see something by eye, we have to consider an exaggerated angular Einstein radius of 100 milliarc second, which is not a realistic situation. But nevertheless, Roman should be able to see even a very small shift of the order of 1 milliarc second. So even if we don't see it by eye, in principle, Roman should see it. So this figure was shown yesterday by Sebastiano Calchinovati, and it is a prediction of the astrometric precision of Roman as a function of the magnitude of the star. And you can see here that for a 21 magnitude star, we expect an astrometric precision of 1 milliarc second. It should be a bit better for the brighter star, a bit worse for the fainter star. What can we do with such a precision? Actually, if we consider 1 milliarc second precision, of course, we have observations like that. So it is too low precision to observe a centered shift in in an individual measurement. But with the cadence of 15 minutes, we have nearly 100 images per day. And so, as was shown by Chris before, actually, by averaging on 100 measurements, we can reduce the uncertainty by factor 10. So if we take the average of all these measurements, we have a red cross like here. So we are detecting actually the centroid motion, taking advantage of the number of measurements. But of course, we are doing a simplistic hypothesis that this uncertainty only comes from a statistical Gaussian noise, which is of course not completely true. So it's in order to do good astrometry with Roman, it is very important to have a good understanding of all systematics. Otherwise, this game would not work, of course. Another factor we have to take into account is that blending by unresolved sources reduces this. So the centroid motion is washed out if we have blending by unresolved sources, or even the lens itself would be a disturbance to the signal of the centroid motion. So what can we expect to see with Roman? So this is just almost back of the envelope calculation to understand which fraction of events we expect to show any astrometric signal with Roman. So I just used a very old galactic model by Dominic. And in this case, you can see that an angular strain radius of 1 milliarc is already quite large for typical microlensing events, which would have a lower angular Einstein radius. So if we the number of the astrometric detection that we expect is very sensitive to the threshold we have for the angular Einstein radius, and this depends on our understanding of systematics, as I said before. So if we keep an optimistic threshold of 0.3 milliarc, then most microlensing events would be also detected by astrometry. But you can see that just by increasing the threshold to 3 milliarc, then the number of detection would drop to just a few. So it's very important to push our understanding of systematics as far as possible, if we want to use astrometry for a good fraction of events. Okay, so the information in astrometry, as Chris said before, the astrometry may yield the angular Einstein radius. In particular, it is well suited for nearby massive lenses. And in this sense is complementary to final source effect, which is, instead favors small and far lenses. And in this regime of nearby lenses, also we are in an optimal regime for annual parallax measurement. So in this case, it's very likely to have, if we have an astrometric detection, it's very likely that we also have a parallax measurement and we can get the mass. There is a good synergy with lens flux measurement, but of course, in that case, we must have luminous lenses. And as we said before, if we have a luminous lens, then blending would wash out the signal. So the astrometry would mostly suited to dark lenses. So and it will give an alternative channel to measure the mass of black holes or other stellar remnants. In order to do that, we must do simultaneous modeling of photometry and astrometry, and in principle, additional effects must be taken into account, such as final source, limb darkening, binary of planetary signals, parallax, orbital motion, etc. And in this respect, then the code that we developed in the last few years is now very well, is very popular in the microlensing community. So it is a microlensing code, including advanced methods. So it's a very robust, very stable, and very fast. It's a public code. It's written in C++. It is importable in Python. And in practice, all current publicly available platform doing microlensing, such as Pylima, Mulan's model, and Mulan, have adopted this VV binary lensing code as their core code. And this is also this will be also used in for the development of the Roma microlensing pipeline. Well, just a few details. Well, these are technical details about the code. It uses a basic algorithm for lensing inversion by Scoren and Gold. The integral over the source sites is performed by contour integration. Then in this calculation, we also include a parabolic correction to increase the accuracy. There is error control, and the sampling is optimized so as to increase to do the calculation only when it's really needed. Limb darkening is included by repeating the calculation. And also there is a decision tree in order to decide whether to go for the full finite size calculation or stay with the point source calculation. Higher orders are also included in the code. And in particular, in the case of single lens and finite source effect, the calculation is extremely fast because the code uses a pre-calculated tables of elliptic integrals. So in this case, it's almost immediate. In the case of binary lens, as Chris showed, the trajectory of the centroid can be very complicated because we have caustics and the appearance of images. Creation and destruction of images produces sudden jumps in the light curve. in this case, the finite source effect is also important because it washes out these jumps, as you can see from this picture here. If you increase the size of the source, then all these jumps become smoother. And the limb darkening can also have a very small impact in this case. It leads to small adjustments of the light curve depending on the coefficient of limb darkening. But this can be taken into account in the book. Okay, and this is just an example of use of the code showing that it's a very simple coding in C++. So you just specify the parameters, define the library, then call the function, and then you get the output. So it's very easy to use, and everyone can try its own modeling of photometric and astrometric signal. So coming to conclusion, as we see, the potential of astrometric microlensing by Roman is very, very interesting. In principle, by the large number of measurements, the dense sampling of Roman, we can detect astrometric signal. But in order to do that, of course, we need to have a full control of systematics. Otherwise, things wouldn't go very, very well. And if we manage to lower the accuracy threshold down to less than a milliseconds, then we can expect even hundreds of thousands detections, and that will make this technique very promising for the measuring masses of many microlensing events. Okay, of course, this is particularly aimed at dark lenses, for which we cannot use other methods to measure masses. So for black holes, stellar remnants, but even brown dwarfs, as Chris showed just a few minutes ago. And of course, so in this talk, I have advertised this code, and here you can see the GitHub link and the publications explaining how BB binary lensing works. And so I hope that this will be useful to the whole microlensing community, also contribute to enlarge the microlensing community to newcomers. Thank you very much.
Thank you, Valerio, and perfectly timed. So we have time for a quick question, and I would like to take the chair's prerogatives, since I don't see some questions in the chat, to invite you to comment on the big data challenge of the modern surveys that are coming up. And I know this is, you have the RT model system that has gone some way to answer the challenge of not just modeling a single event, but modeling hundreds, thousands of them. Would you like to comment on scaling up that solution to the Roman era?
Okay, thank you. Yes, in principle, modeling a single binary event, an individual binary event, takes something like 2 hours on my workstation. So in principle, I suggested that between one season and the other, we can remodel all microlensing events. And this is possible with just a few workstations in principle. So this would be very useful to have an understanding of what we are doing season by season. So I think this is possible and this is feasible. And of course, if we also have astrometry, this can give an additional constraints and also help in microlensing interpretation. We should not forget that sometimes we have degeneracies in the photometric light curves that can be broken by astrometry. So this can be a very useful add-on.
Absolutely. Thank you. And in the interest of time, I think we should move on to our next speaker. So thank you again, Valerio.